is Henk. I work in Chalmers University of Technology, which is in Gothenburg, Sweden. So this map shows here Gothenburg as this, which is the second largest city in Sweden after Stockholm, of course. And this picture in the bottom is a picture of Chalmers when it is both snowy and sunny, which is not a very common combination. And I am part of the communication systems group at Chalmers, where we have 9 professors working in various areas of physical air communication, including wireless and fiber optical, information theory, coding theory, hardware limited systems, and so forth. And within that group, I lead the activities related to radio localization and sensing. I just want to also present my research team. So we are a quite large team with several postdocs and PhD students. We work in 2 areas. For about 75%, I would say we work on radio localization and sensing, mainly in the context of 5G and beyond 5G systems. And then the remaining 25% works on artificial intelligence, mainly deep learning for physical air communication, both wireless and fiber optical, mainly for dealing with hardware impairments. And one of the reasons I show my team is that to show that we have a lot of capacity for doing collaborations, and we are very happy also to set up collaborations with research groups all over the world. So please, if something that I talk about sounds interesting today and you want to reach out, please do so after this talk. So before I go into the more technical aspects of the talk, I first want to motivate why we do this research. So why are we working on these reconfigurable intelligent surfaces, which are expected to be one of the enablers for 6G, for localization and sensing? And the reason is that within 6G, there's a variety of use cases foreseen where 5G just doesn't cut it in terms of the KPIs for positioning. So I showed just here some selected use cases, for instance, cooperative driving, augmented reality, and robot-to-robot interaction. And I will not walk through all of these requirements, but as you can see, the localization accuracy requirements, update rate, and scalability requirements are far beyond what 5G can offer. And these are some of the example use cases that are being studied in a large European initiative called Hexa-X. So if you do not know this, Hexa-X is a so-called flagship project from the European Commission, which aims to define vision for 6G from a European standpoint. This project will end in June, but now the second version, Hexa-X2, has started. And I think it's worthwhile to follow this if you're interested in localization sensing, because it's one of the important topics being studied. In this figure, I try to put 6G in a context with respect to previous generations. So on the x-axis, you see localization uncertainty. On the y-axis, different deployment areas, indoors, urban outdoors, and rural outdoors. And vertical lines represent different use cases. And the different blobs, they represent different radio technologies. So you see, for instance, here, GNSS, including GPS, can cover most of the use cases, provided they are in a rural outdoor environment where you have sufficient number of satellites in view. Then you see 4G and 5G providing progressively better accuracy, ultra wideband, and finally 6G, for which the vision is to provide centimeter level accuracy by 2030. Whether this vision will be realized, we will see in 10 years from now, but at least that's our ambition. And the paper listed on the right shows a more detailed summary of all of these enablers, as well as the use cases and the gap analysis with respect to 5G. So with this motivation in mind, let's go to the more technical part. So this is the outline of this presentation. I will first very briefly talk about what is localization 5G and what is the vision for 6G, including the technical enablers and the hardware, the limitations. And then I will move on to the main topic, which is reconfigurable intelligent surfaces. I will assume that you know a little bit about them, but I will provide just a very brief introduction, how they function and how they could be used for localization. And then I will provide a taxonomy of RIS-enabled scenarios that are minimal in the sense that they require the minimal amount of infrastructure. I will then move on to some of the more advanced applications and wrap up with my conclusions. So let's start from the beginning. So this is a slide that I also have in my wireless communication course at Chalmers, where you see a propagation environment, a transmitter and a receiver. And if you have enough bandwidth at the receiver, you would see, after cleaning up the noise, a signal that looks like this. So you see, as a function of time, the multipath components coming in. The first multipath component could be the line of sight path, and this tells you something about the distance between the transmitter and the receiver. And then all of these other peaks, they correspond to objects in the environment. So all of this information tells you something about geometry, it tells you something about distances, so it tells you something that is useful for localization. Of course, practical receivers don't have such high resolution, so you rely on different other measurements such as signal strength, time-based measurements, or angle-based measurements, which we'll see in a second. Once you have those measurements, then you should put them together to compute the user location. And inherently, this is a statistical estimation problem, so we can rely on the very rich literature from that field, including Fisher information analysis for deriving fundamental insights and doing system design, a variety of algorithms, including maximum likelihood, convex optimization, and Bayesian tracking. You can do signal optimization for positioning, and you must deal with all kinds of practical aspects such as synchronization and calibration. And the nice thing about the positioning field is that whatever people have developed for communication, including MIMO, massive MIMO, millimeter wave, terahertz, reconfigurable intelligent surfaces, and so on, although they have been designed for improving communication data rates, they are also typically useful for improving positioning. So let's look at these different measurements in a little bit more detail. So the first one was signal strength. So if you've taken any wireless communication course, you've seen, of course, the path loss equation, which tells you that the received power decays with distance. And this figure here on the right shows as a function of distance, the path loss, so how much power we lose with distance. And the lines represent these theoretical equations. However, when you look at measurements, things are more blurry. And from a given amount of path loss, it is actually very hard to infer the distance. And for that reason, received signal strength is very rarely used as an indicator of distance in practice. The only exception is perhaps when it is combined with fingerprint. A more practical kind of measurement that is used is time-based measurement. So the figure on the right shows a base station and a user. Typically, if the user is not synchronized to the base station, at least not to the extent that it's useful for positioning, which means that when the base station sends a signal and it arrives at the user estimates the time of arrival, and this time of arrival would be the distance between the base station and the user over the speed of light plus a clock bias. And this clock bias you must always deal with, and you must estimate this. The same happens in GPS as well. If you're more mathematically inclined, we can look at the left side. So suppose you have an OFDM signal, you send a bunch of pilot signals across the subcarriers, then at the receiver, after processing, on the end subcarrier, you would have the channel gain, the pilot symbol sent over that subcarrier, and then a linearly increasing phase with a subcarrier index. And this phase depends on the propagation delay, so which includes the distance and also this clock bias. You can then write this as a vector, and then by taking this vector and doing an FFT and looking for peaks, you can have a rough indication of the distance. We can then complement this with angle measurements, including angle of arrival and angle of departure. So the figure on the left shows how angle of arrival works. So suppose you have a mobile phone with a single antenna far away from a base station with many antennas. Then the signal that arrives across the antenna elements at the base station is affected by small phase changes because the signal arrives first at one antenna and a little bit later at the second antenna and so forth. If you write this down, you have this observation model here where R is the observation across the antennas, alpha is a complex channel gain, and A is the so-called steering vector of the array. And this steering vector here has as argument theta, which is the angle of arrival of the signal seen from the base station. And this again has a similar structure, so you could do an FFT, look for peaks, and then find the angle of arrival. A little bit less intuitive is angle of departure. So now we have a base station with multiple antennas. This base station sends a signal across all of its antennas called S, and then this signal arrives at the user side, which has a single antenna. So the user just observes a scalar. So this is this product of the steering vector times the signal S, complex channel gain, and noise. It turns out now when the base station sends different signals S of t across time, the user can collect discrete time observations, which over time are sufficient to estimate this angle of departure theta. So it's the same angle as on the left, but now it's an angle of departure because of the signal departing from the base station to the user. Maybe it's not very intuitive how this works, but a simple example would be as follows. Suppose that S of t is a directional beam, and the user and the base station agree beforehand to send directional beams in different directions. The user just measures the signal strength, and then the direction with the maximum strength would give you an indication of the angle of departure. You can then put those angle and delay measurements together in different ways. So for instance, if you compute delay time of arrival measurements that are affected by a clock bias, you can compute the so-called time difference of arrival positioning. where the user is on the intersection of different hyperbola. If you do RTT measurements, so you do round trip time measurements, then you can compute the user as being on the intersection of different circles. If you compute angle of departure measurements, then the user is on the intersection of different lines, and any combination of the above. Mathematically, all these problems have the same form. So there's an unknown x, let's say the position. F is a nonlinear function, for instance, distances to different base stations, and then n is noise. And then the observation given in total is y, and then the positioning problem is really to recover x from y. And this is a conventional nonlinear least squares problem that you can solve with a variety of techniques. So how does positioning work in practice? The most common technique is time difference of arrival. So we have here 3 base stations, which are perfectly synchronized and connected to a fusion center, and then a single user. And here di denotes the distance between the user and base station I. If the user sends a signal in uplink, then base station I would measure the time of arrival. And this time of arrival is the distance over the speed of light plus the clock bias of the user plus noise. And it's important to note here that the bias is common to all of the base stations because they are mutually synchronized. To get rid of this bias, we compute differential measurements, taking one of the base stations as a reference. Then the bias is no longer there. And now this differential measurement is really a difference of distances. And this determines geometrically a hyperbola. And that's what's shown here on the right. So there are 3 base stations, and these 3 base stations together define 2 hyperbola. And then the user must be on the intersection of these hyperbola. And now you see that these hyperbola are not really very fine mathematical objects, but they are blurry. So the user is somehow constrained to lie on a large region. And then the size of this region depends on the base station placement, the number of base stations, the bandwidth, and a variety of other factors. If we now look a little bit more in depth what those factors are. So the localization performance is determined both by the performance at the link level, so between any transmitter and any receiver, as well as the system level, so the geometry and the overall system, including all of the base stations. And there's different factors that affect performance, for instance, noise at the link level, and noise can be mitigated by having more transmit power at the base station or longer integration times. There's also multipath, which is the effect that objects will create other paths which would interfere with the line of sight path. And this can be mitigated by improving the resolution, for instance, by allocating more bandwidth to the signal. There's also limitation in terms of accuracy, which can be mitigated by having more power, longer integration time, or optimized waveforms. So that's what you can do at the link level. Now let's look at the system level. What could happen, for instance, is that the path between a base station is blocked. And the way to deal with that is just by putting more base stations to have more line of sight links. You can also have limited accuracy because of the base station placement. And again, the way to deal with that is to put more base stations and optimize their placement. And finally, there could be issues related to infeasibility. And again, these are addressed by putting more base stations and optimizing their placement. So this means at the system level, the only thing you can play with is just by putting more base stations and figuring out where to place them. And this is not a very desirable solution. So to address this, in 6G, people have been looking at a variety of technical enablers. And I could spend an entire talk talking about each of them, but today I will only focus on the 8th enabler, which is the reconfigurable intelligent surfaces. Nevertheless, let me just briefly mention the other enablers within 6G that are foreseen. The first one is that there will be a variety of carrier frequencies. So there will be your traditional FR1 and FR2 at 6 and 28 gigahertz, as well as possibly sub-terahertz transmissions in D-band. And what is nice for positioning is that the higher you go in carrier frequency, the more geometrical the channel behaves. So you will see the individual rays resolved, and they are all tied to geometric objects in the environment. Another benefit when you go to higher carrier frequencies is you will have large aggregate bandwidth. So this is our second enabler. And with large bandwidth comes high delay resolution. So this is very important for positioning. And this is one of the main advantages, for instance, of radar, which rely on several gigahertz of bandwidth. The third enabler, which also relates to the use of higher frequencies, is that to overcome high path loss, you will need multiple antennas. Multiple antennas, both at the base station side and probably also at the user side. Once you put antennas at the user side, you also have the ability to estimate the orientation of the user device. So then we go, and this is shown somehow on this right side here, we go from 3D positioning, so X, Y, Z, to also 6D positioning, including now also the 3D orientation. Another enabler, this may be another very new enabler, is the use of side links, which are coming back in vogue. which will provide relative positioning between devices and then will support cooperative positioning. Another enabler is the introduction of self-free massive MIMO systems, where you will have lots of access points around each device. This will maybe be phase coherent, and this phase coherency provides a large aperture for positioning. A very interesting, and I think underdeveloped regime. One of the topics that gets the most hype these days is the integration of sensing, localization, communication. So how communication can help localization, how location information can improve communication, and so forth. The seventh enabler is the use of AI. AI is being considered across the protocol stack for solving all kinds of problems for which we have a model or an algorithm deficit. And finally, the introduction of reconfigurable intelligent services to shape the propagation environment. With all of these enablers, there are, of course, important challenges, and I just want to highlight here two of those because I think they're often neglected. The first one is hardware impairments. As we go up in frequencies, hardware impairments will start to hurt us more and more. And I believe that they will be more severe for localization and sensing than for communication. The reason being that for communication, you care really about the end-to-end channel after it has passed through all of the hardware. And if you can estimate this end-to-end channel, you can communicate over this channel. While for localization and for sensing, we care about the angles, the delays, and the Dopplers hidden inside of this channel. And then if you're very much affected by hardware impairments, it becomes very hard to extract this information. The second challenge is as follows. If we envision for SIG-G to have centimeter level positioning accuracy, which is really extreme performance, we also need extreme calibration. We need to know exactly where is our infrastructure, where are the base stations, what is the tilt of the antenna panels, in order to enable this very high accuracy for positioning. And all of these enablers, as well as their challenges, are studied in several projects. And I just want to highlight here some European projects because maybe you're not aware of them. So for instance, there's the RIS-6G project, which is studying RIS. There's a Locus project, which studies localization, of course. And then there's the HEXA-X projects, which are the flagship projects providing the overall vision. But so here are just some examples of work that we are doing in each of these areas. I don't want to dwell on that. Rather, I want to start looking into this 8th enabler, so the reconfigurable intelligent surfaces. So let's start with the basics. So a reconfigurable intelligent surface is the meta surface that comprises many small elements, and each of these are controllable. And this controllable nature of these elements allows you to create non-natural reflections. So controllable reflections in arbitrary directions. Since the object itself is passive but controllable, it doesn't introduce any noise. And the most common use case for these reconfigurable intelligent surfaces is to overcome line of sight blockages. That's what's shown here on the right. So there's a source and a destination. The line of sight is blocked, but there is a propagation path from the source to the intelligent surface to the destination. And then the intelligent surface can control and adapt itself to create a high power beam towards the user, towards the destination. And this way we can overcome the line of sight blockage. And these benefits can also be used for localization and for sensing. So for localization, it then becomes obvious we can also do localization under line of sight blockage by using these surfaces. Or if these surfaces are very large, we could use wavefront curvature to have a better estimation of the location. Many of these applications of reconfigurable intelligent surfaces for localization, for sensing, and for SLAM have been covered in a magazine paper, which is now a few years old, but I think it's still relevant today. Going in a bit more mathematical detail, so this is how the communication people see RIS, and this is a figure that I stole from this paper from 2019. So suppose you have a base station, a bunch of users, the line of sight is blocked between the base station and the user, but we have this reconfigurable intelligent surface in between. So then there's a channel from the base station to the surface, HBR, a matrix if the base station also has many antennas. There's a channel from the surface to the users. This is now a row vector if the users have a single antenna element. And then the surface itself can be controlled by this matrix omega, which is a diagonal matrix, which in this case is just a phase rotation. So we can control each of the elements in the surface by a phase rotation, which can then give us a different end-to-end channel, which is with this omega in between. And now it's important to know that all of these elements are on the unit circle. They could also be smaller in magnitude, but they cannot be larger in magnitude. Otherwise, you would amplify the signal and you would introduce noise. So by having them on the unit circle, that's somehow the best case. We can now control this omega and then maximize the end-to-end channel. If the line of sight is also there, then we can just add it, of course, in the expression. The benefit of this RIS, as I tried to emphasize, is that they are nearly passive. They're just controllable. And ideally, they don't need any dedicated energy source. I think that's maybe overstating it. You probably need a controller that controls the RIS dynamically. Otherwise, it just becomes like a reflector ray. So when we now change the perspective and think about localization, the only thing that really changes is how we perceive the channel. So while a communication person would just see this as an unstructured matrix and as an unstructured vector, from a localization perspective, we think about the angles, delays hidden inside of this channel. So the equation at the bottom is basically the same thing, but I just look at what's inside of this channel. So if this is a pure line of sight channel, HBR will actually comprise a complex channel gain, a steering vector at the base station, which depends on angle of departure, which is known because typically we would know where the base station and the surface are. Then at the surface, there's an angle of arrival, which is also known. Then we have omega, of course, the RIS phase control. And then we have the channel from the RIS to the user, which has also a channel gain, and then an angle of departure, which is unknown. And this angle of departure is a thing that we're interested for localization, because once we know this, we know that the user must be on a line away from the base station. Well, today I will mainly talk about so-called reflective RIS. I think it's also important to know that there's different versions of RIS. There's hybrid RIS, which can both reflect and also process the signal locally. The RIS can also act as a lens, so by focusing the signal on the other side of the RIS. For reflective RIS, there are two common operating regimes. So the most common one is the far field regime, shown on the right, where the angles of departure and arrival are the same for each of the elements in the RIS. But if the RIS is large and you're close to the RIS, then you would operate in the near field, so where the angles of arrival and departure at the RIS depend on the specific RIS element. Nevertheless, today I will focus mainly on reflective RIS and work in the far field. So how can we use RIS for localization? So these are some examples, and later we will see them in a bit more mathematical detail. The first example will be the following. Suppose you have a single antenna base station, a single antenna user, and a RIS. If there's no RIS, then you cannot localize because the user and the base station are not synchronized, so you have no location information at all. But when you put the RIS there, all of a sudden you have two propagation paths, so you can compute a time difference of arrival. And if you carefully control the RIS, you can also estimate the angle of departure from the RIS to the user. And this turns out to be enough information to localize the user. If the line of sight is blocked between the base station and the user, still you can do localization if you exploit the near field effect. So the wavefront curvature is also sufficient to localize the user. And finally, you can even do localization if there's no base station at all. And the way that this can be done is when you have a full duplex user. So if there's a full duplex user sending a signal over the environment and the RIS scatters it back, then you can estimate the distance to the RIS. And if you again control the RIS in a smart way, you can also estimate the angle of departure, and you can localize the user. I just want to point out that all of these require that you have RIS configurability that changes over time. So if the RIS is just fixed and has a fixed profile with a fixed directionality, that's not sufficient to solve any of these localization problems. All you can get is an SNR gain and maybe better timing estimation. To really harness their power, you need to have different configurations over time, and the user should process those to estimate the relative angles or positions. If you then want to think about how a RIS at a system level behaves, I think one way to see it is as an additional synchronized base stations with a simple phased array. So this figure on the left shows a room, an environment with a base station and a single RIS. And then I show in colors how well you can be localized in this environment. Okay. If the RIS is not there, you cannot be localized at all. But when you add the RIS, it acts like a secondary transmitter, even though it scatters back the signal from the primary transmitter, the base station. But this provides enough information to be localized. And you see that you can be localized quite well when you're close to the RIS, but the further you go away, the worse the localization is. And it's better to be close to the RIS than close to the base station. And this is just because of path loss. You have the lowest path loss when you're close to the RIS. If you don't want to have a kind of uniform coverage, what you should do is put several RIS in the environment and control them in a smart way, and then you can have kind of good localization performance everywhere. So this was a little bit of the basics. Now let's go towards the main body, which is this taxonomy of different RIS-enabled localization problems. And the reason that we study this is that when you think in a 5G way, then for localization, you need many base stations. So for communication, you need one base station to have a communication link, but if you want to localize yourself, you will need at least 4 base stations to have enough information. While in 6G, we want to still have good communication capabilities, but maybe we don't want to have all of those base stations around, which are costly and consume lots of energy. And so the question is then, can we replace some of the base stations with RIS? And then natural next question is then, what is the minimum number of base stations and RIS that we need to localize the user in different scenarios? And to answer this question, we will make some assumptions. So we will assume that we know where the RIS is. We assume that each of the RIS has a controller that is connected to the network. The user is not synchronized to the network. We will operate in the far field. And we'll break this question down into several cases. So a SISO case, a SIMO case, MISO, and MIMO. We'll walk through all of these in detail. And again, we'll focus on those minimal problems. What is the minimum number of base stations and RIS is needed? And finally, we will distinguish 2 scenarios. So a narrowband scenario and a wideband scenario. Even though as localization people, we like to work in the wideband regime, meaning that we have an OFDM system and we can estimate delays and also resolve delays. Most communication people like to work in the narrowband regime, so where there's no subcarriers and there's no ability to estimate delays. So I will consider both of these in the following slides. Okay, so let's first talk about SISO. So when we have SISO, the base station and the user each have a single antenna. And if we then have a wideband system in which we can estimate delays with OFDM, for instance, then we need 4 base stations, right? We need 4 base stations because each base station gives us a time of arrival, but we also have the clock bias. So we have 4 observables, the 4 time of arrivals. We have 4 unknowns, the 3D position and the clock bias. If you go to a narrowband regime where you don't have any ability to estimate delays, the problem is fundamentally not solved. So now the question is, if we add a RIS, how many base stations can we remove? And it turns out the answer is we can remove 3 of the 4 base stations. So with 1 base station and 1 RIS, we have enough information to localize the user. We will see in detail why in the next few slides. It turns out, as I said, that even if you remove that remaining base station and you have a full duplex user, you can still localize the user. When we go to narrowband, so in the case where we cannot estimate delays, in that case, the problem is not solvable when we are in the far field. When you're in the near field, again, you can solve the problem. Of course, then with 2 RIS, the problem is solvable in the wideband case, but also interestingly, in the narrowband case, the problem is solvable. So with a single antenna base station, a single antenna user, and 2 RIS, you have enough information to localize the user. The reason is that from each of the RIS, if you configure their profiles over time, you can estimate an angle of departure in azimuth and elevation. Okay, and then from 2 RIS, you have 4 observables, 2 angles in azimuth and elevation, and you have only 3 unknowns, the position. In this case, the clock bias is no longer unknown because you don't estimate any delays. So let's now focus on this intriguing case of a single base station and a single RIS in the wideband regime. And now we go into the more mathematical part. And for you, it's I guess, early afternoon, but for me, it's past 9 o'clock. So let's see if I can work through this. So we have the base station with a single antenna, the user with a single antenna, and the RIS. The base station has a certain position PB, the user has an unknown position P. And then we have 2 propagation paths in this case. Of course, in practice, you would have lots more propagation paths due to objects in the environment. We will just focus on this simple problem here. So there's the red path, the line of sight path, which provides only delay information so that we can estimate this tau B. And then there's the green path, which goes via the RIS to the user. It also has a certain delay, tau R, which we can probably also estimate. And then there will also be a directional information from the RIS. Since we only have a single antenna, all we can do is send OFDM symbols, and we can send a bunch of them over time. So in this case, we send T OFDM symbols, each of them with N subcarriers. And that means at the receiver side, we have an observation matrix, T by N, which has 2 parts, the line of sight path and the path via the RIS plus noise. In this case, the line of sight path has a complex channel gain, which is unknown. And then we have this delay steering vector, which depends on the tau B parameter. And this delay steering vector is just a linearly increasing phase with a subcarrier index. For the RIS path, we have another complex channel gain, which we don't know. We again have a delay steering vector, and then we have a vector which depends on the angle of departure. Okay, and if we look in detail what this looks like, it is a steering vector depending on the angle of departure, the RIS configuration, and a steering vector depending on the angle of arrival at the RIS. But again, this angle of arrival is known because we know where the RIS is and where the base station is. So what we want to do now is estimate tau B, tau R, and the angle of departure at the RIS, while alpha RIS and alpha line of sight are nuisance parameters. But again, in principle, we have 4 geometric observables, the 2 delays and the angle of departure and elevation, and 4 geometric unknowns, the position in 3D and the user clock bias. How we solve this estimation problem is as follows. We first split off the line of sight path. So this can be done in several ways. The way that we've done it here is we create a so-called temporally balanced RIS profile. So you send a number of RIS profiles, and then for the remaining time, you send a negative of those RIS profiles, and then you can actually remove out the RIS path. Once we've done that, we estimate the line of sight delay using standard processing, for instance, using FFT, and also estimated channel gain. This channel gain is easy to estimate because it's a linear parameter. Once we've estimated those, we subtract them from the original observation, and if we do a good enough job, all that is left is the RIS path. And here it's really important to do a good job because a small error here will lead to large interference in the remaining part. So now with this RIS path, we need to estimate the time of arrival and the angle of departure. The way that we can do this is estimate first the time of arrival with the FFT, and then for the angle of departure, we do a simple 2D search over a finite interval. So now we have all the 2 delays and we have the angle of departure. From the 2 delays, we can take their difference, and this determines a hyperbola here, as shown in red. Of course, in 3D, it will be a hyperboloid. So it's a 2-dimensional shape in a 3-dimensional embedded world. From the angle of departure, we have a line, right? We know where the RIS is, we know the orientation of the RIS, so we can compute a line away from the RIS, which should go through the user. And then the intersection of this hyperbola and this line determines a unique point, and that's where the user is. So that's how we can solve the localization problem. Let's see now on the right how well we can solve this problem. So the first figure shows on the x-axis the distance of the user from the RIS, and on the y-axis the localization error and also the clock synchronization error when we convert it to meters. And we see basically a bunch of curves almost superimposed, so they are both the estimator and the corresponding Crib-Merrill bound. And what we see is when we are not too far away from the RIS, we can localize ourselves with an error below 10 centimeters. When we get far away from the RIS, the performance degrades. And there are 2 factors causing that. The first one is that you have more path loss because you're further away. The second one is that when you can estimate the angle of departure with some error, the further you are away, a small angle estimation error leads to a large position error, right? Because the angle is shifted, so you have a large position error. Okay, we get this performance because we can do good delay and angle estimation. Let's now look how well we can do delay estimation. So we have again here the distance of the user from the RIS, and on the y-axis the error converted to meters, so by multiplying by the speed of light. And we see here in yellow how well we can estimate the time of arrival of the line of sight path, and then in red and blue how well we can estimate the time of arrival of the RIS path. And again, we have the estimator and the bound. And interestingly, so we can estimate the line of sight path way, way better than the RIS path. And the reason is just simply path loss. The RIS path is both longer and then has to go through this RIS, and it's not necessarily amplified by the RIS, so then you have a huge performance penalty. And this relatively poor estimation of the RIS time of arrival is really causing a bottleneck in the positioning performance. And you can mitigate this by having a larger RIS or by having a longer integration time. And finally, the last figure shows the impact of bandwidth. So when we have more bandwidth, how can we estimate the localization, the user location? And we consider both random RIS configurations and directional RIS configurations. Okay, and what turns out is that random configurations are much worse than directional RIS configurations. Of course, with directional RIS configurations, we need to know a little bit of where the user is already. And interestingly, when you have more and more bandwidth, at some point, the performance of the algorithm degrades, even though the bound will tell you things should get better. What is the reason for this? In this case, it turns out to be an effect of beam squint. So when you have lots of bandwidth with a very large array, beam squint will become dominant. And if you don't account this for in your algorithm, you will have a large degradation. All right, so now we have a somewhat deep understanding of the SISO case. Let's look at a bit more sophisticated cases. The next one is the MISO localization case, so where the base station has many antenna elements and the user one antenna element. Of course, in wideband, you can solve it with 2 base stations. In narrowband, also you can solve it with 2 base stations. The reason is that each of the base stations gives you an angle of departure in azimuth and elevation. So you have 4 observables and 3 unknowns, so you can localize the user. It's basically the intersection of two lines in 3D. Now, let's see how many base stations we can remove and replace them by RIS. It turns out you can remove one of the base stations and replace it by a RIS and still localize the user. The argument is the same. You have an angle of departure from the base station and an angle of departure from the RIS, provided you use different RIS configurations over time. Okay, and then again, for the wideband case with the same configuration, of course, you can localize the user. So this is not very interesting because you're just adding more observables and not introducing more unknowns. Let's now look at the more challenging SIMO case, so where the base station has one antenna and the user has many antennas. So then you have this following scenario. And now it's important to note that when the user has many antenna elements, we should also try to estimate the 3D orientation of the user. If we consider the narrowband case, where we can only estimate angles, it turns out that when you have 3 base stations, then it's enough to localize the user and also estimate its orientation. The reason being that from each of the base stations, you can estimate a 2D angle of arrival, azimuth and elevation. So 3 base stations with 2 angles gives you 6 observables, and you have 6 unknowns, right? The 3D position and the 3D orientation. For the wideband case, also you need 3 base stations to solve the problem. Okay, and how many base stations can we remove in this case? For this SIMO case, it turns out we can remove 2 of the 3 base stations and replace them by a RIS. How can we do localization now? So now we have an angle of departure from the RIS, phi1, and we have 2 angles of arrival at the user side, 1 from the base station, 1 from the RIS. So we again have 6 observables and 6 unknowns, so the problem can be solved. You may ask yourself, is it possible for the user to separate those 2 paths and estimate those 2 angles? And in fact, here a RIS can really help. A RIS can be encoded in a smart way over time to provide increased resolvability between the line of sight path and the path via RIS. Okay, now again, we go to the last case, the MIMO case, which is again an easier case. So in the MIMO case, we estimate the 3D position and the 3D orientation. The base station has many antenna elements. The user also has many antenna elements. So in this case, we have 2 angles of departure, giving us 4 observations, 2 angles of arrival, giving us another 4 observations. So we have 8 observations, 6 unknowns, easy peasy localization problem solved. Again, we can replace one of the base stations with a RIS, and then in this case, we have again 4 angles of departure, 4 angles of arrival, again, azimuth and elevation, so we can solve the localization problem. So now you say, yes, you can argue that you can replace base station by RIS, but can you actually get better performance, right? Is it better to have a base station or better to have a RIS? So let's try to answer that question, or at least think about this. So let's focus just on a simple narrowband case where we have 2 scenarios. So scenario A, you have 2 base stations with many antenna elements, and then you can localize the user with angle of departure from the 2 base stations. Scenario B, you have a SISO case with 2 RIS, and again, you localize the user from the angle of departure from the two RIS. So the localization process is really similar, but which one is better? You could argue that scenario B is a cheaper scenario, right? You have just a single antenna base station emitting a pilot and those 2 RIS, which are largely passive, so it's much more cost efficient and energy efficient. But what about the accuracy? And now there are 2 arguments. So in terms of the SNR, scenario A is clearly better, right? You have a 1-hop link from the base station to the user. But when you think about angle resolution, maybe scenario B is better because a RIS can have hundreds or maybe thousands of elements and can give very high resolution angle of departure. So which one is better? I think there's no answer. It really depends. But I think there are cases where scenario B is preferred over scenario A. This is a more detailed list of all of these scenarios that we've studied, which you can find in our Wymeersch Technology magazine paper, which I think has appeared or will appear really soon, where we study these cases in much more detail. We've also done a practical demonstration of RIS-enabled localization. So this is just a very small setup on the order of a few meters, where we use a unit from Sieverts semiconductors, and we create a kind of fake RIS by looping back the receiver array back to the transmitter array. In this case, each of the RISs is really small. It's an 8x3 array. So in the figure on the left, you saw a base station emitting basically a tone. And then you have the 2 RISs, which are reconfigurable, of course, and changing their configurations over time. And then you have a user which tries to estimate the angle of departure from each of the RIS. And in this case, you can imagine each of the RIS acting like a lighthouse. So the base station illuminates them and the RISs are reflecting in different directions. And the user just measures the signal power. And when the signal power from a certain RIS is really large, that tells you the angle of departure from that RIS, and same with respect to the other RIS. And then overall, by looking at when the signal power from both of the lighthouses is as strong as possible, that tells you something about both of the angles of departure, and then you can localize yourself. And we've done this here, so you have the two RIS, and this shows how well we can localize ourselves. And in this case, we can localize ourselves with an error of about 10 centimeters. Of course, this is with a very, very small RIS. If you have a much larger RIS, you can do much better than this, but this was just a proof of concept to show that it's possible in practice to solve these minimal localization problems. In the last 5 minutes, I just want to talk a little bit about the more advanced cases, just to give you some inspiration for future research problems. So one of the problems that we've been studying a little bit is near-field localization. So where you have the base station, the RIS, and the user, but the user is in the near field of the RIS. In this case, the line of sight path can be blocked. And again, by changing the RIS configurations over time, the user can collect enough information to localize itself. Another problem we've been studying is the localization under hardware impairments. So since these RISs are just put in different places and maybe not monitored or taken care of very well, it's possible that over time there's some impairments, like a RIS element fails or there's other dirt on the RIS. And then we've tried to do localization under those hardware impairments and even try to identify the failures of the RIS. In all of the works I presented so far, I've always assumed that I know exactly where is the RIS and how it's oriented. And that's actually a very hard problem. You can probably assume that people who install base stations do some effort to localize them in an absent frame of reference, but maybe not when you put up a RIS. And not knowing the RIS position orientation is not very critical for communication, but for localization, it's very important. So there should be ways to automatically calibrate the RIS location orientation. And we've made some progress on this, although this turns out to be a very challenging problem. On the right, I show an example of how to use RIS with sidelink. Again, there's no base stations, but there could be, for instance, two vehicles communicating with each other, and the propagation paths also go via the RIS. And in this case, also, both users can be localized even without any base stations, just with the aid of two RISs. Also, this turns out to be a very challenging problem to solve, at least computationally, involving high-dimensional search. So if you could come up with a smarter algorithm to solve this problem, I would really welcome this. And then finally, I want to talk a few minutes about RIS for sensing. I deliberately didn't mention much about sensing, and here I mean radar like sensing, and let me now explain why. When you think about communication, the path loss between a transmitter and a receiver is proportional to 1 over the distance squared. But when you think about radar, especially monostatic radar, the path loss is proportional to 1 of the distance to the power 4, right? Because the signal has to go from the sender to the object and back to the radar. And then now, if we put a RIS in this scenario, we create several propagation paths and several possible combinations. So suppose the vehicle on the left has a radar, is emitting a signal, and it hits the vehicle on the right, scatters back and goes back to the radar. So then this path, direct path, has a d to the power 4 path loss. Already pretty bad. And now we add the RIS. So now we have, for instance, a path A, B, C. This path has d to the power 6 path loss. So it's much, much weaker. And you have two measurements, right? Because you have the line of sight path and the path via the RIS. So you need to deal with those two measurements. And you could even have a path A, B, D, E. So without the line of sight path, and then you could argue, okay, if the line of sight path is blocked, we have this additional path. But this additional path is d to the power 8 path loss. So it's very, very weak, and probably will be drowned out by all of the other paths. And it's interesting that there's been some work on RIS for sensing, but they study a single target with directional beams. I think to really study, you should look at several targets at the same time and solve all of those difficult data association problems. We've done a little bit of study towards this direction. This is a paper we submitted for the ICC workshop, where there's a user trying to sense an environment, different objects in the environment, with the help of a RIS. And now we see that immediately there's different propagation paths again arising. There's a direct path from the radar to the object back to the user in red. There's the path from user to RIS back to the user. There's a path from the user to the RIS to the object to the user, and also a path from the user to the object to the RIS to the user. So if all of these paths arrive at the receiver at the same time, there's basically 3 paths for each of the objects. Okay, and you need to deal with those paths. And among those paths, by far the strongest will be the red one. Okay, this direct path will be drowning out all of the other paths. I had some curves on the right, but I'm running a little bit low on time, so I will not go through them in detail. But the conclusion is that the only way that the RIS is really helpful is when the RIS is very close to the sensor. So you can imagine putting a very simple radar sensor with a single antenna and then the RIS right next to it, then you can have some benefits for radar. But if you put the RIS far away from the sensor, probably the path loss will drown out everything. So now let me wrap up with my conclusions. So I've talked a little bit about the use of radio signals for localization. They've been around always, and as we go to higher frequencies with more bandwidth and many antennas, things are becoming very interesting for localization. Localization needs more infrastructure than communication, and RIS could be interesting technology to replace some of those base stations while still providing good localization quality. There's many interesting research questions that appear by introducing RIS, and I've been surprised for the past few years. Whenever we say, let's put a RIS there and see what happens, we end up with very strange problems that nobody has ever thought about. Nevertheless, hardware limitations will probably be important when you introduce RIS for localization, and we should not ignore them. Knowing the RIS position orientation is something important when we want to do localization, and not very obvious to solve. And as I said, I'm somewhat skeptical for using RIS for sensing. Nevertheless, RIS is just one of the many enablers that I listed earlier, and I could give a 1-hour talk on each of those. So I think really we can say that despite radio-based positioning being around for many, many years, a golden age is just about to begin. And this will wrap up my talk. I just want to acknowledge some of my collaborators and funding agencies. And if you want to know more, you're welcome to check out my website, YouTube channel, or some of the projects where we are involved in. So thank you. I think I'm more or less on time.
Great. Thank you very much, Henk. That was an excellent talk. Very, very insightful. You certainly did not disappoint. We appreciate it. And again, thank you for doing this so at after 9 o'clock at night your time. It's
my pleasure. Very
gracious of you. I have 2 quick questions, and then I unfortunately have to run to
sure.
I'm a little bit late for that, but I wanted to hear the whole thing. So 2 quick questions for you, and then I'll cede the floor to somebody else. First, have you looked at the multi-user problem? When you have now multiple signals arriving at the RIS with potentially different angles of have you thought about that much?
Yeah, we thought about it. So we mainly look at downlink scenarios where you can do broadcasting, and then you can localize all of the users at the same time. And then in uplink, we mainly looked at just time division, that we don't have the superposition of signals from different users, or that users use a kind of orthogonal coding that they can be separated, so that we never have to deal with kind of the superposition and non-orthogonality between the users. So we've looked at it, but only to that extent.
Okay, and so you're sort of orthogonalizing the users to some extent.
Yes.
Now, what about actually controlling the RIS parameters? I guess that would require the time domain orthogonality so that you can change the parameters for the different users, or are you assuming that the users are more or less co-located or nearly co-located?
So again, we've looked mainly at broadcast scenarios. So the base station is illuminating the users and the RIS is just randomly flickering.
Mm-hmm.
But of course, in a known pattern, and that way all of the users at the same time can be localized without any prior knowledge of where the users are.
Okay.
If you, of course, have prior knowledge, then you could focus beams towards the users and have an increased SNR.
Right. Okay. I was thinking more the uplink scenario where maybe they're using SNR to tweak the RIS to essentially steer it.
Yeah, but the downlink is much easier, so we focus on the downlink scenario. Yeah, okay. It's an interesting question.
Yeah. All right, well, one more question. This is a little bit outside of your talk, so you're free to say I have no idea. But you mentioned at the very beginning the potential for AI or machine learning in localization. I'm just curious your opinion. Do you see a role for it in localization? I mean, obviously, when you talk about Wi-Fi positioning and fingerprinting, where they're collecting data, then that makes some sense. But more generally, moving forward, do you see a role for data-based approaches?
I think there are some problems that are really difficult to solve with model-based signal processing, and then AI can shine, of course. Of course, fingerprinting is one of algorithm. I think also kind of processing of high dimensional data and looking at fine grained details of the kind of image processing way. And then finally, I think that's another thing that we've been studying is look at hardware impairment. So you have kind of nasty nonlinear and linear components all concatenated together, and it's very hard to process that with model-based processing. And then doing a kind of, for instance, end-to-end learning to learn spatial signals, to learn how to do processing, turns out to work really, really well and beating all kind of model-based processing. So we have been focused on that.
Okay, so but mostly not so much using it to determine your position so much as learning channel more generically, learning the hardware, those kinds of things.
Or dealing with the hardware. It's not learning, it's really to do the localization under the hardware impairment. For instance, if you have an array and the element spacings are slightly perturbed, how should you do localization? And then with end-to-end learning, you can learn optimal precoders and at the same time, an optimal localization algorithm.
I see. Okay,
yeah.
Great. Well, thank you very much.
Thanks, Mike.
It's good seeing you, Henk.
Nice to see you. Enjoy your soccer.
Thanks.
Bye.
Thank you, Dr. Wymeersch, for your talk.
Thank you.
So I have one question. So you said that the angle of departure at the RIS cannot be estimated with a single RIS profile, right?
Right.
Can you show that? Can you prove that?
Sure. Yeah, sure, of course. So suppose you have, you see this equation on the bottom right, RT is alpha, you see the equation, right?
Yeah.
Yeah, so if you had a RIS, you would basically have the same things. So suppose the user has a single antenna element and then it observes this signal. Let me just put the laser pointer again. It observes this kind of signal plus noise, right? And in this case, A of theta would be the RIS steering vector, and then theta would be the angle of departure from the RIS to the user. Now, if S of t is constant, you have no way to separate alpha from theta. You have no way to separate the channel gain from the angle of departure. So you need several of these distinct S of t's to make it work. And the S of t here plays the role of the RIS configuration. Right? Because if S is constant, it's impossible to separate those two parameters. All you get then is a complex number, right? R, which is basically always constant but plus noise. And from one complex number, you cannot estimate one complex number and a phase, right? It's impossible. All you can get is one complex number. So yes, fundamentally, it's impossible.
Okay. Then
yeah, it's a good question. I mean, people don't typically understand it. So.
Also, so I have a second question. You talked about the RIS misorientation, right? That's the orientation offset that goes with positioning the RIS. Do you know under what situations you can estimate the orientation offset of the RIS?
Yeah, so we studied it. So to estimate the orientation of the RIS, right?
Yeah.
Yeah, so we studied here in a number of cases. So I think the easiest way to do it is you have a calibrating agent or a second base station, so that you have a bunch of reference points, and then you send signals via the RIS, and the RIS kind of cycles through some phase configurations, and then over time you have enough information to figure out this orientation. But as I said, these are really challenging problems. We just have some initial work on this. I think this is largely an open problem.
Okay. Thank you.
Thank you.
Audience, do we have any other questions?
Dr. Wymeersch, I also have two quick questions. If you can go
Sure.
to page 25. Yeah, so in the SISO case, could you explain again? So first of all, why do you need 4 base stations to localize the user? I thought 3 would be sufficient.
It's because the user is not synchronized to the base station. So suppose you only had one base station, right? You estimate tau1.
Okay.
If you were perfectly synchronized to the base station, then tau1 would tell you the distance, right? And then you're on a circle or a sphere around that base station. Agreed?
Yes.
Yeah. But since you're not synchronized, this tau1 actually you're on an infinite number of spheres around the base station, right? Depending on what your clock bias was. So you have an additional unknown, and that's why you need a fourth base station. The same happens exactly in GPS. You need 4 GPS satellites to solve for X, Y, Z, and your clock bias. But after you solved for it, you're synchronized to the GPS satellite. And same here, after you solve it, you're synchronized to the base station. So putting the clock bias there is very important, and this requires this additional base station.
Okay, I see. Oh, one more question is, could you explain again what is the difficulty of the challenging of the narrowband localization application?
I mean, the cross on the left here?
Yep.
Because when you have narrowband and single antenna, then from each of the base stations, you just get a complex number. And there's no geometry, right? Because you don't have any delay. There's no angles because you don't have any antennas at the base or antenna arrays at the base of the user. So you just get a signal, which is a channel coefficients times something you transmit plus noise. But there's no geometry at all that you can use.
Okay, I see.
So there's no localization problem fundamentally to solve. Well, as soon as you have arrays, then there's angles, and those angles you can use to solve the localization problem.
I see. Thank you. So to reconfigure like the faces in the RIS, how do you really program it? Is it being done some kind of like a meta surfaces, or what is being programmed? How does it?
I think okay. I think there's different technologies. So you can have like impedances that you set or voltage controls that you set at each of those elements. So I don't know, that's more of a hardware aspect. So for me, they're just phases that I can control. I don't worry about the underlying means of doing that. So I'm not the right person to ask that question.
Okay, thank you. Thank you so much.
Thank you. Any final question?
I also had a question.
Yeah.
So you said at the beginning of the talk that we need centimeter level accuracy. So will there be any constraints in terms of the delay of localization?
What do you mean here by the delay? Like how the time it takes between requesting the location, their location being available, or?
Yes, exactly.
I mean, there's requirements on that delay, right? Because if you want 1 centimeter accuracy and you move at some speed, then you need to get this information before you move away. So yes, I think that the lower location uncertainty you demand, and the higher the velocity, the stricter you are in terms of latency. So all of these things are connected. And we have some very beautiful figures talking exactly about this in this paper here on the right. So there's some diagrams showing exactly this trade-off between accuracy, velocity, and latency.
Oh, so and does RIS actually increase latency probably
it does, because the RIS, although it can be reconfigurable, it can probably not be reconfigurable at a OFDM symbol level, let's say. If the OFDM symbol is 8 microseconds in 5G, a RIS can maybe be configured every 8 milliseconds, for example. So then it's 3 orders of magnitude difference. So I would say that RIS used for localizations may be better for kind of slowly moving things that require high accuracy.
Okay, thank you.
Thank you. Good question.
I have a question on if you can go, I don't know which slide number it is, but where you had the equation with the omega matrix.
There's a bunch of them. Like when I first introduced RIS, or when I talk about the localization problem. So probably I have this one.
Yeah, that one. Yeah.
Okay.
So for this one, right? Because you say that omega is a diagonal matrix. But isn't it? Don't you have m by m elements? So wouldn't it be like a? Because the faces can be programmed in each.
Sure. So the RIS has m elements. So in this case, it will be 4 by 20, let's say. So M is 80.
Oh, okay.
So yeah, it's a bit misleading, but yeah. So M is the number of elements. So each of them is controllable.
Okay. So it's okay. Thank you. That's
It's not that you can only control the diagonal elements of the resource.
Right.
Yeah.
But so basically, you have M elements total.
Yes.
Thank you.
And each of them is individually controllable, just like a phased array.
Makes sense. Thanks.
Thank you. There was some echo locally there.
Any other questions?
Can I ask one more question?
Sure.
So going back to Dr. Viewer's question about multiple users. So I mean, don't we configure the RIS according to each user? So how then in the case of multiple users, how do we configure the RIS?
Yeah, so I would say, and again, like I said, like it depends if you're in downlink or uplink. So let's look at this scenario here, right? You have these K users and you want to localize all of them. Yeah.
Okay.
So what the base station would do is it would just send a broadcast signal, right, to all of the users, and that allows all of these to estimate the line of sight delay. That's it. And then what I would do with the RIS, I would use a sequence of configurations, and let's say each configuration is directional, just to make it simple. So they first send the beam in this direction, then in this direction, then in this direction, so that no matter where the user is, they will always be illuminated by a few beams.
Oh. Okay.
And then over time, once RIS has done all of these beams, each user has enough information to be localized. This is maybe not the most optimal way to localize multiple users, but in principle, that's how you could do it. So just by having kind of broadcast beams by the RIS. Of course, if you know where a certain user is and you care only about one user, you would do a directional beam like this. If you care about two users, you could do so-called multi-beam. So that's a beam which has two main lobes towards multiple users. That's possible too. So I think there's lots of alternatives for localizing several users. In downlink, in uplink, the story is completely different.
Thank you.
Okay. But then in uplink, what is done, for instance, in 5G is that users would have orthogonal sequences, or you would use orthogonal time frequency resources, and that could still hold even with RIS, so that doesn't change anything. So for that reason, I think the multi-user localization problem is not the most interesting problem to solve, even though it sounds interesting. I don't think it is.
Thank you, Dr.
Thank you.
Hi, Professor. Am I audible?
Oh, still some echo. You can also put your message in the chat if it's.
Hello.
Hello. Yeah, I don't hear you very well, but yes, hello.
Yeah. So I just wanted to know if we generally employ any signal processing techniques at the RIS, and other than the localization, what are the other techniques that RIS can play major role?
Other than localization, so what is the use of a RIS other than for localization? Is that the question? So
my first question is,
yeah,
do we deploy any signal processing techniques at the RIS?
But okay, okay, let me answer one question at a time. So the RIS is a kind of DOM object, right? So it doesn't do anything. All it can do is have controllable beams. So the only thing that you could think about in terms of signal processing is a signal design question. What is the best possible beams that the RIS should use? And for that, you would use a kind of, for instance, Fisher information theory to minimize position error bound and find optimal RIS configurations. I think that's the only signal processing problem at the RIS side itself. Of course, at the user, you need to do the the channel parameter estimation of the positioning. Is that okay for the first question?
Yeah. Yeah. My
Okay,
second
that's good.
question was what are the other techniques where risk can play a major role in other than the localization?
Well, okay, I think for localization, RIS has a good use. For, as I said, for sensing, I doubt it. And then, of course, there's communication, right? The main use of RIS is for communication. And then it's both to create strong beams towards users, but it's also to create, for instance, strong nulls towards users. If you want to have an environment where you want to protect users from electromagnetic radiation, you could actually kind of protect them by sending the energies in other directions. So I think both kind of SNR in a positive and a negative sense. But these are all kind of communication applications. But beyond localization and communication, I don't know. I haven't thought about that. I only think about localization.
Okay, so just one more question extension to my first question. If RIS is not intelligent enough, how do we generally acquire the user information in order to steer our beams towards users? How do we generally acquire the information?
Right, so the RIS is not smart, but it has a local controller, right? So you can imagine that there's some local box here, which is the controller of the RIS. And this controller is somehow connected to the network, just like the base stations. Right, so there's a network, and then each of the users itself through the base station is also connected to the network. So logically, they're all connected to the network, and that's how the network can give commands to the RIS controller, and then the RIS control would be implemented by the RIS itself. So it's just a part of the 6G network.
Okay, thank you, Professor.
Thank you.
I had a question on for the practical experiment, right? How many elements did you use? I mean, I'm sure you actually mentioned it, but I can't remember.
Yeah, so it's an 8x3 array. So it has 8 in the azimuth and then 3 in elevation. So very small. Yeah.
So you have 24 elements.
Yes.
Because I was thinking about the computational complexity, right? If M grows, I mean, then you get like. So I was just wondering, like, what kind of processor did you use? Because if M get large, right, then it will take some time to do all those calculations.
But there's not much calculation going on. So the RIS, as I said, is relatively dumb. All it does is it takes a signal from the base station and it reflects it in some direction. So it first sent here, then here, and it just cycles through all of those directions, and the user just measures the energy. Right, so the processing is really simple. So then the beam with the largest energy, then the user says, okay, I am in this direction. And you could scale this up with more elements. The only thing is it will take more time. Right? The more antenna elements, the longer it takes to go cycle through all of those beams. So this is a bit similar to kind of the initial access from a millimeter wave, where it could take a long time before users find each other.
Okay. Okay, thank you.
Thank you. Good. I think I should wrap up soon here. It's 9:45, and my wife is waiting for dinner. So.
Thank you, Dr. Wymeersch, for your time and for your talk.
Thank you very much. Thank you for inviting me. It was a pleasure to meet you, and I hope we can stay in touch and after this talk too. So.
Yeah, we'll stay in touch.
Thank you. Have a nice weekend, everybody. Bye-bye.